Let us try an example to design an RC staircase. This is the sections of a staircase. The dimensions are given, which is in the form of mm. The dimensions are also listed here. The riser is 175 mm. The going is 255 mm. The thickness of the staircase is 110 mm. There are a total of 10 steps for the staircase. There will be beams in front and at the end of the staircase. And the staircase is connected to the adjacent slabs. In terms of the actions, the GK is 1.0 kN per meter square, and this is excluding the self-weight of the staircase. There will be QK, which is 4 kN per meter square. In terms of the properties of the material, the concrete strength is 25 Newton per mm square. The steel strength is 500 Newton per mm square. The unit weight of the concrete is 25 kN per meter cube. Concrete cover 25 mm, and the size of the reinforcement bar used is 10 mm diameter. You may pause the video for a while for you to work out the solution. For you to design a staircase, you will need to first analyze the actions, the moment, as well as the shear acting within the staircase. Based on the actions acquired, you are able to determine the moment and the shear within the member, design for the main reinforcement bar in accordance to the moment, and then check for the shear resistance as provided by the staircase. Other than that, you will need to check for the other serviceability requirements, such as the maximum and minimum bar area, the deflections, as well as the crackings. Then you are to provide the detailings for the staircase. Now let us start with analyzing the actions acting on the staircase. It is given that the GK is 1 kN per meter square, and this is excluding the self-weight. You know that self-weight is also a part of the permanent action. Therefore, you will need to determine the self-weight of the staircase on basis of the unit weight of the concrete to be added up with that 1 kN per meter square GK and multiply with 1.35 and 1.5 for GK and QK respectively. Now for you to determine the self-weight of the staircase, you will need to use the equations as given here. We have discussed about this in our previous videos, where you can use these formulas for you to determine n, y, as represented in the diagram here. On basis of the y here, you want to determine an equivalent thickness of the staircase, which is taken as the y plus half of the riser. Assuming that the average thickness of the staircase, it will be something like this by definitions of the half height of the riser. And then based on the average thickness, you multiply the unit weight of the concrete, so that you acquire the self-weight of the staircase per unit size of 1 meter width. We know that the riser is 175, the going is 155, and the head shear is 110 as given in the question. Substitute the relevant value into the equation. You obtain the y equals to 133.4. And this 133.4, it will be the y, which is to be added with half of the riser, which is 175 divided by 2. This will give you an average thickness of the staircase of 220.9 mm. Now you can determine the self-weight of the staircase. It is determined by multiplying the thickness of the staircase, which is 2 to 0.9 mm, with the unit weight of the concrete, which is 25 kN per meter cube, and you acquire the self-weight of the staircase to be 5.52 kN per meter square, plus the GK given in the questions. The total GK it will be 6.52 kN per meter square. The QK given is 4 kN per meter square. Now you are to calculate the design load. It is calculated by multiplying the GK with the factor of safety 1.35 plus QK times 1.5. That will give you 14.8 kN per meter square. You know that the design of the staircase is similar to the slabs, which we normally quantify it on basis of 1 unit width. With that, the 14.8 kN per meter square is to be multiplied by 1 meter unit width. You obtain 14.8 kN per meter. Based on the setup of the staircase here, you will see the adjacent slab in front and behind the staircase. There will be beams as a support to the staircase, and you will have staircase here. This will lead to a situation that the staircase is continuous to the adjacent slabs. With that, a free body diagram can be sketched here. This L represents the regions of the staircase, 2 supports from the beam, and there will be adjacent slabs. On such a basis, you will know that there will be moments at the support and also at the midspan. Now we will need to quantify the moment here. To do so, you may refer to the previous slides here, where the formulas of the moments is obtained here. We know that the moment is equals to WL square per 10. The W here it will be 14.8 kN per meter. The L here, it will be calculated from the diagram, which will be determined from the center of the beam to another center of the beam. This will represent the effective span of the staircase. Substitute the relevant value into the equations, you get the moment MED equals to 11.6 kN meter. Having the moment acquired, our next step is to design for the reinforcement bar in resisting the moment. For you to do that, you need to first determine the effective depth of the staircase, which is the D. The D here can be calculated by using the formula here, which is the thickness of the staircase minus the concrete cover and minus half of the size of the reinforcement bar. The H here is given 110. The C here is 25 as given in the questions, and the size of the reinforcement bar it will be 10 mm. With that, your D will be equals to 80 mm. Then you use this formula to find the K. The moment you know is 1.6 kN meter. Substitute into the formula here. FCK given 25. The B will consider in 1 meter effective width. And now the D here, it will be equals to 80 mm. Remember the D here need to be squared. Now you have the K equals to 0.073. This is compared with 0.167, and it is smaller than 0.167. You know that no compression reinforcement bar will be required. You know that the design of the staircase is very similar to the slabs, where you have quite a large cross-sectional area as compared to the loads acting onto the member. It is not likely for you to have the compression reinforcement bar required, similar to the slabs. If you encounter a situation where you require the compression reinforcement bar, there is a likelihood that you might have some calculation steps wrongly computed. You should go back and check your calculation step. Now let us proceed. Having the K acquired, we will need to determine the Z, which is the length of the lever arm. These equations will be used. Substitute the K into the equations. You acquire Z is equals to 0.93 D. This is less than 0.95 D. Therefore, you will use 0.93 D. It is only when this is more than 0.95 you will use 0.95. The Z is limited by a maximum of 0.95 D, which in this case it will be 74.5 mm. Next, we will calculate the area of the reinforcement bar required. Substitute the moment acting onto the staircase, which is 11.6 kN/m, divided by 0.87 FYK-Z. FYK is given 500 Nm/mm², and the Z here is calculated as 74.5 mm. You will obtain the AS required of 358 mm². Now you will provide the reinforcement bar, which in this case you provide Y10-200 that give you the areas of reinforcement bar 393 mm². This value can be acquired from the tables of the reinforcement bar that you use to design for this slab. You are talking about the bar size of 10 mm with the spacings of 200 mm that give you 393 mm² reinforcement bar. The provided AS is now greater than the AS required. You know that the amount of reinforcement bar is sufficient. Next, you will need to check for the AS minimum, which you can use these equations. Determine the FCTM from the table 3.1 in Eurocode 2. This is table 3.1 in Eurocode 2. The concrete strength is 25, FCK equals to 25. Your FCTM will be equals to 2.6. Or you may use the equation here for you to determine the FCTM, which in this case the FCTM is calculated from the equation. Substitute into the equation here. The width here is by 1 meter unit width. The depth here is calculated, which is 80 mm, and FYK is given as 500 Nm/mm². Then you will acquire the minimum amount of reinforcement bar to be 107 mm². Compared with the amount of reinforcement bar provided, your provided reinforcement bar is now greater than the minimum required. Therefore, it is acceptable. Next, you will check for the AS maximum as given by the equation here, which in this case it is 0.04 times the areas of the section. The areas of the staircase is calculated by the width 1 meters of the staircase times the thickness of the staircase, which is equals to 110 mm. you will get the maximum amount of reinforcement bar to be 440 mm square. Compared with your AS provided, and your AS provided does not exceed the maximum allowable areas, therefore it is acceptable. Next, you will need to determine the amount of reinforcement bar on the transverse side, which is known as the secondary reinforcement bar. The transverse reinforcement bar does not contribute resistance to the moment, and you know that staircase is a one-span member. Basically, the secondary reinforcement bar does not contribute to that in terms of the moment resistance. However, it is required in terms of the crack control, and the requirement here, it will be at least 20% of the main reinforcement bar. It also helps to keep the main reinforcement bar together, especially when the workers on site will need to tie the primary and secondary reinforcement bar together before the casting, in order to ensure all the reinforcement bar are at the right positions during the casting. 20% of the main reinforcement bar required for the staircase, it will be equals to 358 times 0.2, that give you 71 mm square. Provide the reinforcement bar on the secondary side so that it is greater than 71.6, which in this case will provide Y10 300. Now that we have the primary and the secondary reinforcement bar design, our next step now is to check for the shear reinforcement. We need to decide whether shear reinforcement is required. The calculation steps will be very similar to the slab. Due to a relatively large cross-sectional area of concrete as compared to the load. This is the free body diagram here. The design load is 14.8 kN per meter UDL, and we know that the moments at the supports are 11.6 kN meter. Use the principles of static equilibrium. Taking the point here equals to sigma fx, sigma fy, and sigma m equals to 0. You are able to determine the vertical force B here. Do the same for the support here. You are able to determine the vertical force A here. We will take this as the maximum shears. From the calculations, we have 20.72 kN shear force per unit width of the staircase. As this is symmetrical, then we know that the shear force at both support it will be the same, and our VED will be 20.72 kN per meter unit width. Now we will go through the checking for the shear resistance of the concrete using the same series of the equations that you use to design the slabs. This is the formulas of VRC. These two formulas are the same, which within the formula here, you have K, you have rho, you have SCK, you have B, and you have depth. The K is given by the equation here, which is in the functions of the effective depth. We have the depth calculated previously, which is 80 mm. Substitute into the equations, we get our K equals to 2.58. This is greater than 2.0, therefore we will use K equals to 2 as limited by 2.0. Next, we talk about the amount of reinforcement bar of the sections as represented by the rho 1. It is calculated by having the amount of reinforcement bar provided divided by the width of the staircase times the depth of the staircase. The AS provided here is given as 393 mm square. The B is 1 meter unit width, and the depth here was calculated as 80 mm. Substitute all the values, you get rho 1 equals to 0.0049. It is less than 0.02, then you may use the exact value of 0.0049. Substitute the relevant value and you get your VRDC 44.3 kN. The FCK here is 25. The B here is 1 meter width and the D here is 80 mm. Next, you will need to check for the minimum shear resistance of the concrete. The equations is given here. Use the same K as calculated previously, which is equals to 2. Substitute FCK, 1 meter unit width, and the depth of this staircase. You get 39.6 kN. The shear resistance of the staircase, it will be the larger value of these two. That gives you 44.3 kN. This resistance is to be compared with the shear loads which we calculated earlier. From the free body diagram here, we know that the VED is 20.72. Now our shear resistance here is greater than the shear loads. That means it doesn't require additional shear reinforcement for the staircase. Now that we have done checking for the moment and shear, we also done checking for the maximum and minimum bar area, and we done for the shear checking. All this was found pass. Our next step is to check for the deflections of the member. Therefore, we will need to use these equations for us to determine the limits for the L per D ratio. Since that no compression reinforcement bar is required, that means most likely we are dealing with this equation. You may find the relevant value for the rho and rho naught, as well as the K from table 7.4N Eurocode 2. You should first find the rho and compare against the rho naught. If you find the rho is less than the rho naught, then you will use these equations. Otherwise, you will use these equations. But we know that no compression reinforcement bar will be required. Most likely you will end up with this equation. And then the L per D limit here will need to be checked against with the L per D actual. You need to make sure the actual L per D ratio needs to be less than L per D limits. There will be modification factors, which is governed by 3 main factors here. If the span is more than 7 meters, if your steel grade is more than 500, and also if your provided reinforcement bar is more than the required amount of reinforcement bar. Now let us proceed with the calculations. First, you will need to determine the K value. Refers to the setup of the staircase here. You have slat adjacent to the staircase. That means this staircase span is an interior span between 2 adjacent slabs. From table 7.4 and in Eurocode 2, interior span, you know that the K equals to 1.5. Now you need to determine the rho and rho naught. The rho is calculated by the AS required divided by BD. The B is 1 meter width, the D is 80 mm. The AS required is 358. as calculated previously, and you get the value of rho. You compute the rho node by substituting the concrete strength 25. You will get rho node equals to 0.005, which by comparing these two values, you know that the rho now is less than rho node. That means you're going to use this equation. Substitute the relevant value into the equation here. This includes the K equals to 1.5, FCK equals to 25, rho nodes based on what we have calculated, which is 0.005, and rho, it will be 0.00448. Everything, you get L per D limits, which is 30. Now you check for the modification factors. The span of the staircase is 2.8 meters. It is less than 7 meters, therefore there won't be any corrections. The steel grade is 500 mm. No modifications will be required. The AS required is 358 and AS provided is 393. This will give you a modification factors of 1.0978 as a ratio between AS provided and the AS required. This value needs to be less than 1.5. Now the L per D as calculated from the equations to be multiplied with the modification factor, you acquire 32.9. Next, you will need to calculate the actual L per D ratio. The L here refers to the diagram, which is 2.8 meters. The D here is calculated, which is 80 mm. Now the ratio here, it will be 35. You realize that the L per D limited is now less than the actual L per D ratio. That means the member will fail in deflections. In this case, you will need to increase the thickness of the staircase and recheck again for the amount of reinforcement bar as well as the other serviceability requirements. Instead of having the H here 110 as given in the questions, you may need to increase this H here probably to 125 or 150 in order for you to pass for the deflection check. Next, we will need to check for the maximum spacing of the reinforcement bar. You know that the thickness of the slab is 110, which is less than 200 mm. The maximum amount of reinforcement bar will be determined by the equation here. It is only when your H now is greater than 200 mm, then you will use this formula and the table. Since in this case, the H is less than 200 mm, then you use these two equations. For the main reinforcement bar, it needs to be less than 3 times the thickness of the staircase, which is 330, or a maximum of 400 mm, which in your case here, the maximum spacing of the reinforcement bar in the actual situations is 200 mm. The spacing is acceptable. As for the secondary reinforcement bar, the requirement it will be 3.5 times the H as well as a maximum of 450 mm. 3.5H is equals to 385 mm as compared to the actual spacing provided 300 mm, the spacing pass. Now what we see from our calculation steps here, the designs was okay except for the deflections. The member failed in deflections. In this case, we will need to increase the thickness of the staircase. It is only when all the structural aspects as well as the serviceability concerns are fulfilled, the members are considered safe.